Yeah, hello. Well, for me in Germany, it's still good morning. I can say good afternoon to you. And thank you that you made it to my speech. And I would like to say, everybody in Malaysia, thank you for the nice welcome here. And I really like the country. And I'm proud to be here at HITB in 2005. So make this one big. So everybody in the back, can you please dim down the light a little bit? I can hardly see my in Bamberg, Bavaria, Germany, and I have a thesis project in refactoring security, anti-patterns and distributed Java components. But that's not for living. For living, I have to earn some money, and I do security management at a large financial group in Germany. So we do Java and J2E. Corba, design and development, security hardening, and code audit. And there's a nice intersection between these two topics, which I will present in the following slides. So we have to deal with Java everywhere. Java is on the platform, it's J2SE, Java 2 standard environment, but most of the aspects we will see in the demo at the end will also apply to J2E. And Java is designed as a programming language with many inherent security features, like written by Gong and Oaks in the large books. And on the JVM level, you have type safety, bytecode integrity checks. On the API, you have the security manager, the class loader, and the third pass for the certificates. And for role-based access, you have Java authorization and authentication services. And for crypto people, they have the JCE, JCA, and the Java secure sockets. So we shouldn't be exposed to any dangers. We are in a safe environment. So what's the problem? Why do I give this speech here? So there have been there have been some Java security alerts in 2003 until 2005, and there has been a large history of it, like already presented here at HITB from LSD, but the history has continued, and there are now new Java versions out, but these new Java versions also have their security alerts. So applets are still allowed to escalate privileges, and they are still crashing JVMs, still denial of service, and embedded products or browsers, they have their integration problems with Java. So some browsers allow access to Sun packages, and some ports of Java have their own problems, like the port of Java on Mac. So there's a lot of attack potential despite of these precautions in the Java security architecture. And on the next slide, we will go into the reasons and what is behind these problems. So a Java problem, a Java platform, like any other runtime environment, is designed by humans, so it contains errors. The humans are the programmers, and a programmer sometimes have, on a Monday morning, maybe does bad programming, but not the topic here. He may be interested in functionality as application programmer, communication patterns, marshalling frameworks like RMI, Corba, or XML, and security architect, like seen before, uses crypto object and secure sockets to secure the insecure applications designed by the application programmer. And there are always the people who want to break systems with malicious intent, and these are the people, the adversaries, who try to undermine security by finding the one weak spot. And the Java VM and the core libraries, they have a couple of them. So this is the architecture, the security architecture of the class loaders and the protection domain. You see there are privileged classes, the privileged classes which are loaded from the bootstrap class loader and from the extension class loader. They have a parent relationship, and they are on the top. And on the bottom you see the application classes, which are bound in a jail defined by the policy, which is, for example, defined by the applet sandbox or by the application server policy. So an attacker sometimes seeks, or often seeks, the way into the privileged classes to trick these classes into control paths he wants them to use. There are some security bugs not only in your own code, there are bugs in middleware components. You reuse these middleware components in a lot of trusted places, and these are sometimes already loaded by the boot class loaders, where they're very privileged, and can we really trust them? I don't think we can, because they're not really audited for security purposes. So your graphics library may have vulnerable code which can be triggered by an attacker, or your desktop JVM is really secure in isolating your banking confidential data from other malicious applets loaded into the same JVM. Or if your data is transferred via object serialization, so it may be altered, it may be somehow manipulated, so it crashes or it manipulates a remote JVM and does not do what you want to do as a programmer. So Java is not alone on the desktop. Java has found its way from the toast machine to all the other tiers in the enterprise. So it's on the client, it's on the presentation tier, it's on the enterprise tier, and of course it's on the back end. On the client you have the standalone version, standalone client, which talks via ARM directly to the enterprise container, or via HTTP, like the browser client, to the web container. And the web container and the enterprise container, they talk via JDBC to the database. Or the enterprise container may also access some legacy application via J2C somewhere else in the enterprise. So these are, you see the exposure to the user. On the left side you see the applets, then the presentation tier with the JSP and the servlets. On the enterprise tier you have the session beans, the entity beans, and message-driven beans, and on the back end you have the enterprise adapter, enterprise resources, Java stored procedures, and UDFs. So looks like a nice picture, but what can happen? So you have different kinds of attacks, and the denial of service or the malicious serialized data attacks, which can go via data serialization, via object input streams into remote JVMs, or you just fake a client and do functionality on the client side which is not allowed by the official client, but you fake or you recompile and recompose some application so it works like you want and not like the application deployed by someone else. But Sun, as the vendor of Java, has thought about it all, and they designed some secure code guidelines. You see from the last update from February 2, 2000, they did not do many work on this topic since then, but at least they give you these 11 guidelines: careful usage of privileged code, what they didn't do, careful handling of static fields, what they didn't do, reduce scope, what they didn't do, careful select your public methods and fields, appropriate package code protection, use immutable objects, never return a reference to sensible data, never store user-supplied data directly, so careful serialization, carefully use native methods, carefully clear sensitive information, which sounds like a normal common sense behavior, but you find a lot of bugs in the JDK due to violation of these code guidelines. So secure unaware coding creates vulnerabilities. Yes, sometimes. Typical Java secure anti-patterns. So the reverse of the patterns is like ignoring these security patterns, like ignoring language characteristics. So trick into integer overflows or do careless serialization, expose everything on the wire, or careless use of privileged code. So every code runs with all permissions. Inappropriate field and method visibility leads to covered channels, or covered channels may result from non-final static fields which are shared by different applications on the same JVM. Anti-patterns are hide in your own code. That's what you can change, where you can really redesign your code, but they're also what's very difficult in the libraries you use, and there you have to wait for an update, which is sometimes several years away. So due to academic interest, we audited parts of the JDK 124X and present the findings on the following slides. But how did we do it? How did we automate it? Source code detectors. Our source code is very useful, but source code is not what's running on your machine, and often in closed sourced environments you don't have the source code. Decompilers, yeah, they give you a transformation of the bytecode to a readable source basis, but they really don't show what's going on bytecode level. So we choose the bytecode audit analyzers, find bugs, and find bugs we wrote our own detectors with a visitor pattern, and the find bugs framework is based on quality, how to check software for quality, but we extended some detectors for security purposes. And you can put Java programs in a test bed and find out what permission it needs, but for really search for security bugs, we went into the RT-jar and went into the code which is deployed by Sun Microsystems. So that's what we said. It's an open source framework, the find bugs framework, and it's based on BCAL, has a visitor pattern approach, and has a GUI and a command line. But what's most important, it is extensible and allows you to write your own detectors which run through the bytecode, which run through the code which is actually executed. So, and what kind of anti-patterns can we categorize? So we selected a couple of them. So these anti-patterns, bugs and flaws, they are in the trusted code, like the RT-jar. RT-jar, everybody knows the RT-jar of Java. It's the runtime.jar, which really it encloses all the runtime classes that are exposed as the API, like the java.classes, but also internal classes like the sun.classes. So we identified 3 clusters of bugs: availability bugs, integrity bugs, and secrecy bugs. And the availability bug was, for example, triggered by integer bugs or serialization side effects. Integrity bugs were triggered by privileged code side effects, inappropriate scope, or covered channels. And secrecy bugs, there were, for example, exposed to insecure component reuse, like the integration or the insecure integration of the Orc Apache classes by Sun Microsystems. So it was allowed to sniff private XML data between applets. And so we wrote a binary audit toolset to detect these anti-patterns in own and